in Chapter 11, you're going to see a lot of similarities to what we did in Chapter 10. Because just like Chapter 10, in Chapter 11, we're going to be looking at a difference between two groups. The change from Chapter 10 is that in Chapter 10, we constructed confidence intervals to actually estimate what the difference would be between two groups. In Chapter 11, we're going to look at running a hypothesis test to determine if there is a significant difference. Okay, so again, confidence intervals estimate the actual difference between the two groups. Hypothesis test, look to see whether there is a difference or not. So the first example that we're going to be looking at here, we have scores on a national assessment, range from 0 to 500, and we have information about two groups. All right, we have students using a computer. Mean is 309, standard deviation is 29. The other group, we have students not using a computer. Mean is 303, standard deviation is 32. For the students that use a computer, we have a sample size of 60, and for the students that don't, we have a sample size of 40. Now, we can easily look at the sample data and see that there is a difference between the sample means of 6, 309 to 303, but this is just for those samples. We want to know, is there a significant difference between what happens in the population? So if we were to look at all students, not just these two samples, would we see a significant difference? All right, now, just like we did in Chapter 10, we're going to start with independent samples. So notice these are two separate groups that we are comparing. And our null hypothesis is going to state that mu1 is equal to mu2. I lost a little bar there. All right, null hypothesis states equality. The alternative hypothesis will either state that the mu for group 1 is less than mu2, that mu1 is greater than mu2, or just that they are not equal to each other. All right, little review of notation here, but this is the same notation that we used in Chapter 10, looking at two independent groups. And then you see your formula for standard error. Again, that should look familiar. It's the same standard error that we use for the confidence interval. And then how we use that standard error to calculate a test statistic. Now, something to note about the test statistic. Obviously, the first value in parentheses is just the difference between the two sample means. The second value in parentheses, which is what we're comparing that against, looks at the difference between mu1 and mu2. So remember, our null hypothesis is typically going to state that mu1 is equal to mu2, equality. So if you were to subtract mu2 from both sides, this would be equivalent to a statement that says mu1 minus mu2 is equal to 0. And that's what we'll be testing against. When we look at that difference between the sample means, we'll be testing against a difference of 0. We're going to use a t-distribution, again, just like we did in Chapter 10 for the confidence intervals, and the degrees of freedom will be the smaller sample size minus 1. We do have a few assumptions that need to be met to make sure that we can use this particular distribution. Simple random samples, independent samples is what we're looking at here, and then each sample size is greater than 30, or we know that the population is normally distributed. Here's our basic steps, but again, you are familiar with the basic steps in a hypothesis test. Right? You do your null and alternative, you get your rejection region and your critical values, you compute your test statistic, And then you make the decision based on whether you are in the shaded rejection region. All right. So let's look at how we would apply the basic steps for a hypothesis test to the two groups that we were asked to compare here. All right, so we already pulled the important information. We had mean, standard deviation, and sample size for each group. We want to know if the population mean scores differ, right? That just means we're looking for not equal to, right? It doesn't say one's greater than the other or less than the other. If they differ, it just means they are not equal to. And we're going to run the test with a level of significance at 0.05. So what I'm going to do first is just pull the information from each sample. All right, so group 1, the students using a computer. The sample mean is 309. The sample standard deviation S is 29. And the sample size for that group was 60. For group 2, the sample mean score was 303. The standard deviation was 32. And the sample size was equal to 40. All right, so our assumptions are met here. Random samples, independent, two separate groups, sample size, both large enough. And now we are ready to begin our hypothesis test. All right, so null hypothesis is going to state equality. mu1 is equal to mu2. Alternative, in this case, we're just looking for a difference. So it will state that mu1 is not equal to mu2. Next thing I'm going to do is get my rejection region and my critical values. This is a t-distribution that I am using. And remember what I talked about with hypothesis tests before. I like to sketch out the rejection region. It just makes the decision easier to make. So I'm going to sketch out my bell-shaped curve centered at 0. I'm going to look back at the alternative hypothesis to determine if this is a left, right, or two-tailed test. Okay, not equal to makes this a two-tailed test. And so I'm going to shade both tails for my rejection region. All right, now remember when you do this, right, you're going to have one of three options. You'll have a two-tailed test, like what we're doing here, where you split the rejection region, or you might have a right tail or a left tail. You look at the alternative, right, and it tells you where to shade. For a left or a right-tailed test, you will just use the level of significance alpha as it's given. You just have to remember a left-tailed test has a negative critical value and a right-tailed test has a positive. But for a two-tailed test, you have to remember to divide the area by 2. So since that is what we have here, we're going to take our level of significance, 0.05. We're going to divide that by 2, and we're going to use an area of 0.025. Degrees of freedom, we're going to take the smaller sample size of 40 and subtract 1. Now at this point, you can go to your T calculator if you want to use the one in the ALEKS calculator, or you can pull your T distribution table. All right, so I've got my T distribution table here. I'm using alpha over 2, right, which was 0.025. And I am looking for 39 degrees of freedom. That lets me know the critical value for this test is 2.023. Now, this is a two-tailed test, so that means you will include the positive critical value up here on the right side, and you will include the negative critical value down here on the left side. So remember again, just making sure that you put things in the right spot when you're doing your homework. And Alex, what we find using the table or the T-calculator, these are the critical values. And in this case, we have 2, 1 negative, 1 positive. All right, to make my decision, I'm going to need to calculate my test statistic. All right, we've got our formula defined right up here. We start by looking at the difference between the sample means. All right, X bar 1 was 309, X bar 2 was 303. We are technically comparing this against the difference between population means, but because our null hypothesis says they are equal to each other, they technically have a difference of 0. So really, all you end up looking at in your numerator for the test statistic is the difference between the sample means. All right, I need to divide this by the standard error square root, and for each group, we're going to take the variance divided by the sample size. So I'm looking at the square root. I have standard deviation, so I'll have to square them. 29 squared divided by 60. And 32 squared divided by 40. All right, I can calculate this all in one step if I use parentheses, or if you want to do it in 2 steps, just be careful about your rounding. For that bottom value, I'm looking at the square root of 29 squared divided by 60 plus 32 squared divided by 40. All right, that gives me an approximate standard error, and again, I'm just going to make sure I don't round this down too short, of 6.2942. And when I calculate the actual test statistic value, dividing those two things, I get a test statistic of 0.953. All right, we use the test statistic to make our decision. And the way we make our decision, anytime we're using the critical value method for a hypothesis test, is we take that test statistic and we look to see if it falls in the shaded rejection region. In this case, that does not happen, right? 0.953 would be somewhere between 0 and 2, right? The key is it's not in the shaded region. So because this is not in the shaded region, which is what we call the rejection region, we will not reject the null hypothesis. All right, now, to answer our question, can you conclude that the population mean scores differ? We just said that we cannot reject the null hypothesis. And the null hypothesis says there's no difference. It says mu1 is equal to mu2. So because I was not able to reject that null hypothesis, I am not able to conclude that there is a significant difference. So for my interpretation here, I would state there is not enough evidence to conclude that there is a significant difference. And again, this difference that we're looking for here is between the population means. So even though there was that difference between the sample means of 6, our hypothesis test lets me know that this is not strong enough evidence to state that there is a significant difference between those means if we were to look at the entire population.